So today we're going to be talking about probability with like compound events. So just running over a little bit of the vocabulary for you. A compound event or compound probability is the likelihood of multiple events. So it's when you're doing more than one thing at once, right? So maybe flipping a coin 2 times or spinning a spinner and flipping a coin. Sample space, obviously, it's all the possible outcomes, but it's going to look a little bit different with this. We'll talk about that. Independent event is, so what that is the probability of one event is not affected by the probability of another event. So we'll talk more about that. Dependent event, the probability of the second event is affected by the probability of the first event. So we'll talk about that. Okay, so let's go over this example first. Let me slide me down there. Okay, so we've got a tree diagram. We're rolling a fair cube. Basically, all that means is it's like a regular die, like a number cube, 1 through 6, right? Just like the big purple one back in our classroom. So we're taking that and we're rolling it, right? And we're going to roll it twice. Roll it once, pick it back up, roll it again, okay? We want to know what's the probability if the first time we rolled it, we got a 3. And if the second time we rolled it, we got a 5. So we could, if we wanted to, draw out a tree diagram, right? If I get 1 on the first roll, I can still get 1 through 6 on the second roll. Same thing if I rolled 2 on the first roll, all the way up to if I rolled all the way up to 6. And I'm noticing that this graphic, this guy right here should have a 5 in there, right? Instead there's 2 3s. Sorry about that, guys. So if you're like me, you don't feel like drawing out a tree diagram. It's too much work. It's ridiculous. So let's talk about it, how we can do this a lot easier with math, right? And we learned about the counting principle, which is where you multiply. We're going to use that. So let's think about our sample space. We're not going to list everything out, but what we're instead going to do is we're going to think to ourselves, how many possible outcomes are there, right? So you could count all this up and see that there were 36 outcomes, or you could say there's 6 outcomes on the first try, right? 1 through 6. There's 6 outcomes on the second try, 1 through 6. So 6 times 6 gives you 36, right? That's like your total number of outcomes. And we're going to use sample space to represent that right now. When we think about probability, how many of these options start with a 3 and then have you rolling a 5? Well, just one of them. So that probability would be 1 out of 36. But another way you could have gotten this without doing the tree was saying, what's the probability of rolling a 3 the first time? 1 out of 6. What's the probability of rolling a 5 the second time? 1 out of 6. Because there's 1 5 on there out of 6 sides. 1 6 times 1 6 gives you that 1 over 36. All right, let's look at another one. So this one, you roll a fair 6-sided cube. Again, just means a regular number cube, regular die. You want to know the probability of rolling the first time getting a 4, the second time rolling and getting an odd number. Okay, so how many possibilities are there on the first roll if it's numbered between 1 and 6? There are 6 possibilities on the first roll. Okay, and there are 6 ways it could land on the second roll. 6 times 6 is 36. So our sample space is going to be 36. For probability, rolling a 4 the first time. Well, how many 4s are there on a 1 through 6 number die? There's 1. So that probability would be, for the first roll, is 1 out of 6. Then you got to think about the odd. So with the odd, how many odd numbers are there on that number die from 1 to 6? Well, there's 1, 3, and 5. So there are 3. So you would have 1 6 times 3 6, which gives you 3 over 36, or 1/12. So let's look at an example using, they talk about like a box of billiards, right? That just means like pool balls. So you've got 15 balls, number 1 through 15. You've got them in a box. You're going to randomly pull one out. You're going to look at it, and then you're going to put it back. Okay? Notice you're putting it back. That's really important. Then you're going to pull another one. Since you are putting it back, you are not affecting that second sample, right? It's still got all the balls, numbers 1 through 15. So what we call this an independent event. Because what you do, if you pull a 4 the first time, it doesn't affect what happens the second time because you're putting that 4 back. So you still are left with the exact same sample to pull from that second time. So it's an independent event. Our sample space for this, well, how many possibilities, if you have numbers 1 through 15 in that box, how many possibilities are there on your first pull? There are 15. You're putting back what you pick. So how many possibilities are there the second time? Still 15. And 15 times 15, because our counting principle says we multiply, gives us 225. Okay. Now we're going to think about this probability. We want the probability of getting a 9 and then getting a 3. Well, what's the probability of getting a 9 the first time? How many 9s are there if it's number 1 through 15? 1 9 out of 15. So 1 over 15. What about the 3? There is 1 3 in there out of 15 total numbered balls. So 1 out of 15 times 1 out of 15 gives us 1 over 225. So it's a very small probability of getting that exact combination of a 9 and then a 3. So let's look at this guy here. So let me move me again. Sorry about that. All right, so Carrie has a box of cards with letters that spell mathematics. She pulls out a card and does not replace it. So we need to find a probability of pulling, of pulling an A and then pulling a T. So notice she does not replace it. So she's got a box of cards. When she pulls one out, she sticks it to the side. That means when she goes to pull another one, her sample is changed because there's one less possibility in there, the first card she pulled. So what we call that a dependent event. It's dependent because you're changing the sample. So we need to find what is the probability of pulling an A. Well, first of all, let's talk about like our sample space here, right? Like how many possibilities are we going to have? So let's look at how many letters are in the word mathematics. And here's where it gets interesting. So the first time she pulls, remember she's got all these letters in there, right? And if it's multiple times, the letters in there multiple times in the word mathematics, then that means there's more than one card for it, right? So there's 2 M's in mathematics, so she's got 2 M's in the card. So the first time she has 11 cards because there are 11 letters in mathematics. She pulls a card out and sticks it to the side. That means the second time that she goes in that box, there's only 10 cards. That's how the sample space changes, and that's what makes this a dependent event. So let's talk about probability. We want to know first draw. First time she's got 11 cards. What's the probability of pulling an A? Well, how many A's are there? 1, 2. So the first time she pulls out of there, the probability of pulling an A is 2 out of 11. Now she sticks her card to the side. She now has 10 cards. What's the probability of pulling a T? Well, there's 2 T's out of 10 cards remaining. So again, the probability of pulling an A is 2 A's out of 11 cards. The probability of pulling a T is 2 T's out of 10 cards because she never put that first card back. We use the counting principle. We multiply our 2 probabilities. we end up with this number, which we want to simplify. Probabilities are always in their simplest form, so please make sure you're doing that. And we end up with 2 out of 55 is going to be her probability. All right, and then this will be the last one we do together, and then you'll do some practice. So Lisa's a coin with heads on one side, tails on the other side. She's going to flip it in the air 3 times, and we want to know some probabilities, right? So what's the probability of getting tails, then heads, then heads? This is a classic case of independent events, because think about it. If you flip a coin and get heads the first time, then you flip it a second time, can you still get heads or tails? Absolutely. Your sample space is still the same. You haven't changed your sample, right? There's still 2 possibilities. No matter how many times you flip it, there's still 2 possibilities. That's an independent event. So what's the probability of getting tails? 1 out of 2. What's the probability of getting heads? 1 out of 2. What's the probability of getting heads again? Still 1 out of 2. Counting principle says we take that and we multiply, and we end up with 1/8. A lot of people want to add these, right? Or they think it's 3 1/2 and they give like 1/6 or 1 and 1 or 1 and 1/2, right? No, it's 1 out of 8 because it's 2 times 2 times 2. Looking over here, tails, 1/2. Heads, 1/2. Tails, 1/2. So you're still a probability of 1 out of 8. All right. So now you're going to go ahead and practice. Make sure you turn this whole thing in when you are done. I love you so much. Reach out with any questions you have, and we're going to work more on this tomorrow as well. All right. Thank you, my sweethearts.